In the last chunk, we talked about a principled way to attack the radioactive decay problem, and in fact, a principled way to attack any inference problem. And the purpose of this next section is to dive down into the mathematics of what we've done, and instead of studying the equations, study things in graphical or pictorial terms to really understand what happens when we have a data set in the radioactive decay example and how this shapes the posterior. Before I do that, I want to take a few minutes just to relate this approach using probabilistic inference back to the ad hoc approaches that we started trying to attack this problem with to begin with, and hopefully argue for why the probabilistic approach is more principled and less ad hoc. So in order to do that, what I'm first going to do is I'm going to just do a tiny bit of algebra in order to form this posterior distribution at the top here. So this thing up here. And last time we said we can form the prior using this simple uniform distribution between 0 and 100. We could do other things, but let's run with that for the minute. The piece I really want to focus on is this likelihood term, the likelihood of the parameters, which we said was given by a product of these densities at the bottom here. So for each data point, take the probability of that data point under the model, given the radioactive decay constant, and you product them all together. And this thing, of course, is written down here. It's 0 if the decay events take place outside of the detector. There's 0 probability of that happening. And then for those that do take place inside the detector, the ones we actually get to see, they're just given by this exponential distribution. So this thing will become equal to a product from n equals 1 to n of 1 over z of lambda. That's this term. And then we get the exponentials e to the minus x n over lambda. And we can turn a product of exponentials into an exponential of the sum. And so we can actually rewrite this likelihood term in the following way here. So here I've just collected together all the exponents and taken them inside a single exponential. And notice here we get n lots of the normalizing constant all producted together. So we get z to the lambda raised to the power n, and that comes outside the sum because it doesn't depend on little n. Okay, so this is sort of the form now for the posterior. We've got a prior, a uniform distribution, and then the likelihood function outside. And we're going to renormalize this. We get the posterior distribution over lambda, the probability of lambda given the decay events. Why are we doing this? Why are we drilling down in this in this much detail? Well, what I want you to think about now for a few minutes is, do we need to retain our entire data set to compute the posterior? Do we need to keep the precise values of all of the decay events in the memory of our computer, or can we get away with storing something rather simpler? If you think about that for a few minutes and look at this expression that we have here, you'll notice two things. Firstly, we only need to store the sum of the data points here. We don't need all their precise values, we just need the sum of the decay events. And we also need one other piece of information, which is n, the number of data points. If we have those two pieces of information, we can compute the likelihood term and therefore the posterior. And equivalently, you could also think about this as storing the mean of x and n. If we have the mean of x, then I can replace this sum in here with n times the mean of x. So it's exactly equivalent to store the mean of the data points and just the number of data points. And we could also compute the posterior and the likelihood terms. And this is interesting. It's interesting because if you cast your mind back to the second ad hoc approach we looked at, where we computed the mean of the decay events, and we used that estimator as a method for inferring lambda, that same statistic, the mean of the decay events, has popped up in Bayesian statistics. So that statistic has special status given the modeling assumptions that we've made. It was the right statistic in some sense to retain. The method which we use to work backwards from that statistic to an estimate of lambda here is quite different from that ad hoc approach. But Bayesian inference here has given us a way of determining which estimator we should retain from the data. The mean and actually the number of decay events are the natural statistics to retain. The method then for estimating lambda is now this probabilistic thing, so it is quite different. So in that sense, it justifies one of the aspects of that second ad hoc method and fixes the other aspect, which is to say that we've got this more principled way of working from the statistic back to a actual now distribution over lambda. With regard to the first ad hoc method, which used bins, there's no bins in this method, so there's no need to take our data and transform it in any way, or to lay down arbitrary bins. There's also no arbitrariness in terms of a cost function that we've used to measure the quality of our estimate for lambda. That all just arises naturally from Bayesian inference and the modeling assumptions. We don't need to make any additional assumptions beyond that sort of given in the question itself. So for both of those reasons, the probabilistic method is arguably more principled. I've also talked about these other arguments based on Cox's proof of consistency, and also an argument that we'll meet in the next video chunk or so about betting arguments for why this is sort of an optimal way of going about things. Okay, so that's why this is to be preferred over the ad hoc methods. Let's now turn to considering actually deploying this method on a particular data set, and to try and understand how the posterior arises and intuit why the sort of the Bayesian calculus, the sum and the product rule, gives sensible plausibilities of lambda given a radioactive decay data set. And I'd like to start by thinking about this by going back and just doing a really simple thing, which is to plot some of the densities, which are specified by our model. So let's pick a particular decay constant. So I've picked lambda is equal to 5 centimeters here, and I've plotted the model with that particular decay constant in. And I plotted it between, if you look at the bottom axis here, between 5 centimeters here and the end of the detector at 50 centimeters. Of course, outside this range, the probability of observing any data is, of course, 0. So I could have extended this out here, but we're not allowed to see data outside of this region because a detector doesn't extend there. So this is our model for lambda is equal to 5. Let's look at this model again for a slightly different setting of lambda. This is where lambda was equal to 10. And hopefully you notice a few things. So the decay constant now is a bit bigger. So the exponential decays a bit more slowly. It's lying above the light blue line at this point because the decay constant's a bit bigger. But then because this thing has to normalize, the area under this solid blue curve has to integrate to 1, just like the one under the light blue curve. That means that the normalizing constant is a bit bigger, and it means that the density around 0 is a bit smaller. So the curve sort of shifted down. In this region, it's lying below the light blue line, and in this region, it's lying above the light blue line. And that's all because of this normalizing constant in here, which we said looked like something like lambda e to the minus 5 centimeters over lambda minus e to the minus 50 centimeters over lambda. That's what that's been dragged down here is due to this normalizing constant that we computed earlier on in the lectures. And we can make it again a third plot here for an even bigger normalizing constant, an even bigger setting of lambda, which results in a bigger normalizing constant. This is lambda equals to 20, and you can see a sort of a similar effect. Things are dragged down on this side because the normalizing constant is a bit bigger, but they're higher at the other end of the detector. Okay, so this should be fairly simple and intuitive, but it has a really important consequence. This behavior where the density in this region is going down as lambda increases. So on the left over here, let me just point out, in this region, the density is getting lower as lambda increases, and in this region over here, the density is getting bigger as lambda increases. That will have some consequences when it comes to applying Bayes' rule that we'll see in a minute. Okay, so that was the density. Now we're going to focus on the likelihood terms. And this is sort of a fundamental switch when we're thinking about Bayesian inference that is important to get your head around. So remember the formula for Bayes' rule. Let me just recapitulate it at the top so we've got it in our head. It says that the probability of lambda given all of our decay events, this is just rewriting stuff we saw on previous slides, is, let's call this proportional to, let's forget the normalizer constant for a bit, is proportional to P of lambda times the product over n P of xn given lambda. So when we're doing inference, Basil said we have to use these densities, these P of xn's given lambdas, but these are now fixed. Xn is now fixed, and it's given by the observed data. And what we're viewing this as a function of now, we're viewing it as a function of lambda. Now view as a function of lambda. And this is the fundamental switch. Before, on the previous slide, we're viewing P of x given lambda as a function of x. And we're pretty familiar with that, and everything's sort of fine and dandy and fairly clear. Now, the way it participates in Bayes' rule is that we view it as a function of lambda instead, and x is fixed to the data. And here I've made a plot of that. I've changed the x-axis here. It's no longer x on the x-axis, it's lambda on the x-axis, measured in centimeters. And I've plotted it for a particular data point, an xn, where xn is equal to 15 centimeters. Okay. And so we're now going to vary lambda with xn fixed to 15 centimeters, and varying lambda will change the term in the exponent, and it will change the normalizing constant, because the normalizing constant depends on lambda. And there we see a surprising thing happen. What happens is it starts off really, really low. It has some peak, and then it tails off again. And so if we were sort of considering how this contributes to the posterior, this says that settings of lambda in this region around here are very compatible with our data. Remember, our data point sits here. This is sort of x equals 15 centimeters, just shown it on the same plot, because it has the same units as lambda. And it says that, you know, settings of lambda that maybe 15 centimeters and a bit lower, 12 centimeters or so, are really compatible with your data point. Settings of lambda which are close to 0 are really completely incompatible with x is equal to 15 centimeters. These things will, well, if the decay constant was so small, we'd only expect to see data in the detector around 5 centimeters, because the exponential decays away so quickly. Very long settings of lambda, so say lambda is equal to 100 centimeters, are kind of compatible with the data. They're not ruled out by the data like lambda equals to 0 is, because if the normalizing constant is very big, you expect to see data throughout the detector at 5 centimeters and at 50 centimeters. So what we're going to do now is try and figure out precisely why this peak occurs in the middle here at around 15, maybe 12 centimeters. Why does that end up being the most probable or the most compatible setting of lambda with the observed data point at 15 centimeters? So let's go back to our density plot to really understand why that's the case. Here is our x equals 15 centimeters location. And again, I've shown the 3 densities that we started plotting to begin with for lambda equals to 5, lambda equals to 10, and lambda equals to 20. And you'll notice that the scaling of the normalizing constant that we talked about earlier will have a really important effect. So first off, let's consider the lambda equals to 5 curve. This is the lambda equals to 5 centimeters curve. You'll see that this is quite a small decay constant, and so it decays quite far down by the time it reaches x is equal to 15 centimeters. And so x has relatively low density under that model. Let's consider now the black curve, where lambda is equal to 20. That's this one here, lambda equals to 20. Here, the decay constant is rather big, so the normalizing constant drags everything down. And we start from a relatively low density at x is equal to 5 centimeters. And although things don't decay much by the time we reach 15 centimeters, again, the density at 15 centimeters is rather low. So again, it's giving comparatively low density to the x is equal to 15 centimeters point. And in between these two extremes, between the very short decay constant And the very long one is the Goldilocks curve. And that's the lambda is equal to 15 centimeters curve, 10 centimeters curve in the middle here. So this doesn't have such a big normalizing constant, so its density at 5 centimeters is not dragged down too far. It doesn't decay particularly quickly, and it ends up giving the most density to x is equal to 15 of these three curves. And it's for this reason that intermediate settings of lambda, which are not too big and not too small, end up being more plausible with the observed data, and they result in this bump in the likelihood function around here. It's the normalizing constant trading off with the exponential term, giving this sort of sweet spot in the middle. So this hopefully gives you some intuition for how these likelihoods of the parameters can rule some parameters in and some parameters out. And in a real posterior, we wouldn't just have one of these, we'd have a whole set of, if you have multiple data points, you have multiple likelihood terms, which are all producting together. So let's look at the effect of what happens with in that case. So here we start with one data point and we form our posterior distribution. So we take, in this case, a data point, we're imagining around x is equal to 20 centimeters as our first data point. This is x1, and we multiply it together with our prior, p of lambda, which we said was a uniform distribution between 0 and 100. That's what's causing this sharp cutoff here at 100 centimeters. And multiply the two together and renormalize, and that gives us our first posterior distribution. And now we can consider seeing a second data point. A second data point comes along. Now the posterior is produced by taking the prior, multiplying it by the probability of the first data point, that's the one we just saw, and our second data point, which has now got a value around 15 centimeters, I think, for this one. And you start to see that the posterior distribution is starting to develop a little peak that's inherited from the peaks in the likelihood functions. The first likelihood function here for x1 is equal to 20 centimeters. It says, well, it's ruled out these low settings of lambda down here, but anything up to 100 centimeters is roughly equiprobable. So it doesn't really tell us much amongst the high lambdas, doesn't really prefer one or the other. There's a slight preference for lambdas around 20, but it's not big. By the time the second data point comes in, the x is equal to 15 centimeters data point, then a peak starts to emerge because its likelihood function is a bit peaked in that area. And then we see a third data point, and the posterior starts to become more and more peaked. And a fourth one, you can see now we're becoming reasonably sure that the value of lambda is somewhere around 10 centimeters. And then a fifth one, and so on and so forth. So because they're all producting up together here in the posterior distribution, these likelihood terms multiply together and they start causing the posterior to concentrate in a particular region of parameter space, indicating that we're becoming more and more confident about the setting of lambda as we see more and more data. Put another way, if lambda was really, really short, we would have expected to see many more decay events around 5 centimeters, and none of these were as small as 5 centimeters. And if lambda was really, really big out here, we'd have expected to see some decay events in the end of the detector, somewhere around 50 centimeters around here, and we see nothing in this data set around 50 centimeters. So these are starting to look like less plausible explanations. We've only seen 5 data points, so they're not completely ruled out, but still we're starting to become very sure about what's going on. The posterior distribution itself is often not what a user wants. And indeed, the radioactive decay question to start with asks for a single setting of lambda to be returned. And perhaps if you return a user a probability distribution, they won't necessarily know what to do with it. But one attitude you can take here is to summarize the posterior. And something that you'll see often done is to find the most probable setting of lambda, which is just the maximum of this curve. So this is called the maximum a posteriori estimate. This is formed by taking the argmax over lambda of the posterior distribution of lambda given the data points. And this is called a lambda map. And you shouldn't just really return a point estimate to people. You really want to return uncertainties. And if you want to do this in a way which doesn't involve returning a full distribution to someone, a sensible thing to do is just to return the full width of the distribution at the half maximum point. For instance, you could return these error bars here to give you plus or minus error bars on the map estimate. There are other ways of summarizing posterior distributions as well, but this is one common one that we'll use in the course from time to time. A second common thing to do, again, this is not going to come up in the course too often, but it certainly will do in textbooks if you read them, is to summarize the posterior using a Gaussian. So a Gaussian with a particular mean and a particular variance, which might be chosen to match the posterior distribution according to some criteria. I'm not going to say too much about that because we don't, as I say, cover it in this course, but it is a common method that you'll find in many of the textbooks. And then a final way of summarizing, again, won't spend too much time in the course, but you'll find it in textbooks, is to return samples from the distribution. So you form your posterior distribution and then you sample from it, like you would sample from a Gaussian random variable or a uniform random variable. Here it will be a rather more complicated distribution that you're sampling from, but the samples can be interpreted by a user as typical settings of the radioactive decay constant, which are compatible with your data. And when you sample from it, you'll get more samples around the peaks than you will in the tails. And the statistics of the samples can be used to compute, say, the mean of lambda given the data and uncertainties in that value of lambda from by looking at the variance, for example. Okay, so that's really the probabilistic approach in a nutshell, explained through the radioactive decay example. And I just wanted to end by summarizing the steps that we've taken. And these steps are steps which you should apply to any inference problem. So whether it be this relatively toy one or the more complicated ones that we considered at the very start of the lecture as motivating examples from climate, physics, computer perception, collaborative filtering, so on and so forth. The first key thing to do is to write down the joint probability of everything. And by everything, I mean the unobserved variables and the observed variables. So in this case, that amounts to articulating the prior over the decay constant, our assumptions about what typical values of that decay constant should look like, and then the model that relates the decay constant to the actual observed data. And this was actually given to us in the question because there's a well-defined physical principle that links decay constants to the decay events, that they're drawn IID and that they come from truncated exponential distributions in this case. So this probability of everything can be viewed as a little way of generating fake data. You could sample from this joint distribution to sample a radioactive decay constant that's sort of typical that you'd expect, and then you could sample fake data from that. So you can view this as a little statistical recipe for generating data that reflects your knowledge about the data generating process. Okay, so you've written down your probability of everything, and then somebody says, I want to form an estimation of a particular parameter. And in order to do that, what you do next is you use the product rule and the sum rule, aka Bayes' rule, in order to form the posterior distribution. And that's this second step articulated in here. And that has a normalizing constant out the front, and then a prior, and then this thing, which is called the likelihood of the parameters. And this is the thing that has this sort of inverse flavor. These problems are often called inverse problems for this reason. In the model, we're viewing lambda as fixed often, and we're generating data from the model. And then when it comes to inference, we're viewing the data as fixed because they're given to us, and we're viewing lambda as variable, as the random variable, if you like. So this is sometimes called inverse problems. And that's why this is called the likelihood of the parameters and not the likelihood of the data. So often people call this the likelihood of the data, and that's a slip of the tongue. It's viewing the probability of the data given lambda as a function of lambda, and for that reason it's called the likelihood of the parameters. Great. Okay, so that's the second step, form the posterior distribution. And then optionally, you might want to summarize that posterior distribution, for instance, by the maximum a posteriori estimate, which is the maximum of that function. And one really important property of the maximum a posteriori estimate is that if you use a wide uniform prior distribution, this will actually correspond to the maximum likelihood distribution at the bottom here. Oh, sorry, the maximum likelihood estimate at the bottom. So the maximum likelihood estimate just focuses on optimizing the probability of the decay events here, the data given lambda. And it doesn't involve the prior. So this term up here, this is equivalent to maximizing, because the normalizing constant here doesn't depend on lambda. The map estimate is equivalent to maximizing P of lambda times P of the data given lambda. And so the difference between these two estimators is just the prior. And if the prior doesn't depend on lambda, because it's a big fat uniform distribution, then the two things will line up together. So the maximum likelihood estimate just concentrates on what the data tells us. It doesn't fold in any a priori knowledge that we might have about lambda, or equivalently, we might assume that lambda comes from a uniform distribution over wide support. Great. Okay, so that's the summary of what you were going to do. And essentially the course is going to look at a whole bunch of different problem settings, and to some extent just apply the same recipe in each one of those settings in order to compute inferences in those various different application areas.